Welcome back. Everybody here?
Hello.
Hey. Okay, so in the second half, we'll try and get into the details of the actual rules of Floyd-Hoare logic. We've done the concepts, now let's look at the guts of it all. What we have here is a collection of rules which together form a logic. So as we've seen in other logics, here we've seen the MIU system, propositional logic, predicate logics, modal logics. This is just another logic. And remember, all the stuff below the line is just a string. So it doesn't matter there are these funny Hoare brackets, they're just symbols along with everything else at this level. Now, as before, there are a bunch of inputs to the rule. So this rule, for example, you need to show, well, you need to prove this, and you need to prove this, and if you can prove both of those, then you can prove the thing below it. Yeah. So if this is a theorem and this is a theorem, then you can add this to your collection of theorems. Each of these rules corresponds to part of the syntax of our simple imperative programming language, apart from this one that I'll talk about separately. This is an imperative language, which means it has state, it has memory. We can assign values to variables and they stay there in the state. And being imperative also means that you can perform commands in a sequence. You can do something, then you do something else, and so on. The rules given here are only for what we've called partial correctness. So you remember, we're also going to have total correctness, which is harder. Partial correctness means if the program halts, then you get your postcondition from the precondition. But it might not halt. Whereas total correctness is going to prove that the halting occurs as well. So we do the partial correct version first, because it doesn't have that extra complexity of showing that the thing halts. Yeah, showing that things halt is going to be generally impossible, right? And we know that already. But in many cases, you can actually do it. So let's try to understand the basic structure. Let's take the composition rule as an example. Let's understand the basic structure of a rule there. So in this case, we've got two inputs. If these two things are theorems, then so is the thing at the bottom. And you can see every formula in Floyd-Hoare logic has this structure. It always has a precondition and a program and a postcondition. It's the string as a whole that makes up the formula. And the P and Q and B and C are meta variables here, meaning that they can be any program. So if you've got a huge long program there in P and another huge long program in Q, then you can conclude that the first program with a semicolon after it, followed by the second program, is also having these conditions, if everything satisfies the precondition. So let's try and understand what this rule is actually doing. Okay, this is describing a property of program composition. So in composition, you've got a program P, you run P, then the semicolon means run Q afterwards. The effect of this then is that you already know that P has a contract. P says that if you start from precondition phi, then you are guaranteed to end up at postcondition psi. Okay. So what does this one say?
If you have the precondition psi, then you can end up at the post condition, and then you execute the program Q, then you end up at the post condition chi.
Yeah, good. So when we put these things together, what does that mean then? Like we've started with phi, yeah? We've run P. Where are we now? What's happened when we run P?
We end up at the post condition phi.
Yeah, okay. And you notice that post condition is the same as this precondition, yeah? So if we started off with the ice cream being white and we've run our program and it made the ice cream yellow, this program takes a yellow ice cream and it makes it brown, say. Okay, so this is bringing together two statements then. The first program takes us from state phi to state psi. The second program assumes that we're in the state that was left by the first program and says we'll go into chi. And so therefore, that's the meaning of the bar in the rule. Therefore, if you start with precondition phi and you run P followed by Q, you can conclude that you're going to end up in state chi at the end. Okay. I don't know if this is the origin of the semicolon or whether the semicolon was invented first and they made the rules to fit around it. But there's a certain justification for both semicolons and curly brackets that shows up in here. You'll see curly brackets making an appearance, and they're quite handy when you're doing this kind of logic. So if you didn't have the semicolon, you'd have to write these with a new line, and that would mess up your nice proof rules. Yeah, the semicolon lets you write two things on the same line, so you have a string here instead of a new line in the middle of it. We have a bit of a getting rid of semicolons and curly brackets obsession around here at the moment. So this is the composition rule, okay? Precondition, intermediate condition, post condition. In fact, this is what justifies what we did in the chopping the chicken recipe. It justifies this idea of writing down these intermediate conditions. And we could equally write the program now as something like P 4 bracket psi Q. Yeah, we could actually embed that assertion in the middle of our program between those two lines. All right, now we have an assignment. Now this is more of an axiom because you can see there are no inputs. This is something that is always provable. And this is defining make x become equal to e. Or very technically make the value of variable x equal to the value of e. And this is done using substitution. This is the same, this means phi with e for x, which we've seen in a whole bunch of other places, like the lambda calculus, alpha conversion, and so on. And it's important to get this the right way around, okay? If you recently had a program which had the value for e substituted for the value of x, you can conclude that after the assignment, so not a program, if you had a state with e for x true, then the state would be true without the substitution. Question from Matthew.
I believe, isn't that the other way around? You're substituting, what you're doing in the program is substituting x with e. So if you have a prior state, and then which had some x's in it, and you replace all of those x's with e's, you'd end up at the post state, right?
Now, I believed that yesterday, and then I convinced myself that this was actually the right way around. let's try and figure this out. Okay, so maybe for example a post condition might be something like x equals 5, and a pre-condition might be something like what could we do? Let's just say e equals 5 to make it easy. And now we say let x become equal to e. Does that
Isn't
make
E a
sense?
constant? The way that I interpreted this is like E is a constant, essentially. And in our precondition, we have a bunch of x's that haven't been assigned. And that's how we end up at the post condition.
Okay, so maybe if you don't like the arithmetic, maybe you want to do a logical one. You know, let's say x and e are just pure symbols, right? So post condition could be that x is red. Okay, and if you take that and make the substitution, you have a precondition. I'm going to look for all the x's there, and I'm going to substitute e. So if it used to be true that e was red, and now we've made x equal to e, it's now true that x is red as well.
I apologize. I just opened Huth. I'm afraid that Huth does in fact agree with me. He says that the way that he explains it is if we wish to show that the precondition holds, if the postcondition holds, then we need to show that in the precondition we can substitute all instances of x with e.
Yeah, so it's phi with e for x. Yeah. So the post condition is x is red, the precondition is e is red. Yeah. Yeah, it feels like it's backwards, but it actually works. Good.
Yeah.
Good. So here we're thinking about the system state. So your model theory then has to give a meaning to all of this. Your model theory has to explain what that actually is. You know, what is this machine that has a bunch of things called variables, and what does it mean for a variable to have a value? And roughly here we're assuming the model is going to be something like a register machine. It's a machine that has a bunch of memory locations. Each one has a name rather than a numerical address, such as x. You know? So there's a pigeonhole with x written on it, and we're going to put values into the pigeonholes. And that's pretty much the state of the whole machine. We don't have any functions in this language, but we do have a program counter, I guess. So you need the state of those variables and a program counter to know where you are in the program. Okay, so the next easiest one is if. So we've actually already seen an example of this because we looked at that simple bit of logic that we did informally. So let's look at the formal version of what we just did. So here's a construct in the language. By the way, these logical rules don't define the language. We're assuming that we already have a language, and we're making some statements about the language, but the statements here are not necessarily exhaustive. So this isn't a full way to define the language itself. We might talk next week about stronger logics that are able to do that. So yeah, we're assuming that we actually already know what an if statement is, and that we have a machine that executes it here. But we can at least make this observation, right? That if this thing is known to be provable, all right, I'll just tell you in advance we're going to be complete and sound. So things that are true and provable are the same. Okay, then we can talk about truth. If this thing is true, then if this thing is also true, then you are allowed to conclude that the thing at the bottom is true as well. So would anyone like to try explaining what is going on in this statement? Then it's what we already did in that example.
I was just following it through. How does chi, the x, get introduced? Shouldn't that be thigh?
I think it probably should, yes.
Yeah, because what you're saying is if the precondition, what is it? It's thigh. Thigh, as in philosophy, is the circle with a stroke through it. So if thigh and b holds,
that one's phi, that one's psi, as in philosophy and psychology. So that's a psi. Yeah.
I've come up with some mnemonic for that. So if thigh and b holds, the program C1 is run, and the state that we end up in is psi. If just the precondition die holds, then the program C2 is run, and we end up in the state psi. So we can combine those and say that if we're in the so we can put the B into the program itself, and we can say that if we are in the precondition psi, which both of the inputs, the priors, what would you call them? Because I don't want to say preconditions. The priors. So if both of the priors hold, if both of those are true, then because they share this this state, this preconditioned state of psi, then we can take that B out of the left-hand side and write in the program that if B holds, then C1 occurs. Otherwise, C2 occurs. And that leads us to the same, this is the important bit, I think, is that leads us to the same postcondition because both of those inputs end up with the same postcondition.
Yeah, good. So there's actually a little bug in my notation here as well. This should actually say phi and not B. This is phi and B, and this is phi and not B. Yeah. So this
that's a really good point.
In the other case. Yeah.
Yeah.
Okay.
Because
good.
I also holds in the other case, doesn't it? Yeah, that's good. Yeah.
Okay. So what's important is that all these logical statements, like phi and psi, they're not necessarily complete descriptions of the state of the machine. They're just statements about it. Okay, so yeah, if you say X is red, for example, or red X, that could be statement phi, and that's a statement about the state of your machine, but it's not an entire description of the state of your machine because there could be a whole bunch of other variables called Y and Z and other predicates and all kinds of other things. That's why this isn't a complete description of the language, because it's not telling you everything that happened. It's just saying that if something happened to be the case before we do all this, if X is red at the start, then you will end up with psi if these other two observations hold. Okay, so can we come up with any meaningful example? The X might be red at the start, right? And C1 might mean paint Y blue, and C2 means paint Y blue as well. And then phi is the statement that Y is in fact blue. So, there's an example where the X started off being red, we ended up with Y blue, and it's just followed from those observations about each of the subcommands. Okay, but it's phi in that case is quite a weak statement. It's just saying, psi is quite a weak statement. Now, psi could just be saying that Y is blue, and it's not even talking about what color X is, because it's not something that we happen to be interested in at the time. If we wanted to use rules like this to define a whole language, which we'll hopefully look at later on, then we have to be more rigorous about keeping the whole system state and showing any side effects that come along. Okay, this is a very simple rule. It looks scarier than it actually is. This isn't defining a language feature, it's just letting us rewrite our preconditions and our postconditions. So you can see the command above and below the line is exactly the same. This could be any program, any command. But it is allowing us to, it's called strengthening the precondition or weakening the postcondition. So you can see if this thing held up, if phi c psi is true, you can make a new statement with a different precondition and a different postcondition. Okay. So did I get that the right way around? If we can deduce phi from phi prime, then we know that the required precondition has been satisfied. Okay, so anything we can say about phi prime is also true of phi. So for example, phi could be x is red, and phi prime could be something stronger. This could say x is red and y is blue, and blue y. Okay, so we've strengthened the precondition. So you know, here we've said extra stuff about the state of the system, but it still implies all the stuff that we needed for this thing to be true. So we can chuck as much extra information in here as we want, and the original 4 triple will still work. And then on the other side, this is weakening the postcondition. So if you've concluded a psi, if you've concluded a psi and then psi in turn implies something else, then you can conclude that's something else. So that's just a basic rule of logic. If you figured something out and that something tells you something else, then you're allowed to conclude the something else. So this makes more sense when you see it actually in a real program, because sometimes you have a very specific requirement in front of your C, and you need to replace it with something more general. And sometimes you have a general post condition, and you want to replace it with a specific one, such as the thing that you're actually trying to prove. So that sounds a lot more complicated than it actually is. You'll see it when we look at a real program, and that's the implied rule. So as with all the rules, we always write their name as a little comment in brackets by the side. That's not part of the logic, that's just for us to remember what the names of the rules are. And it's this one that defines us as being in the partial correctness system. This is the partial correctness rule for while. Now, you could build a programming language that doesn't have this. You could build a language that only has the stuff above it. And what you get then is a language that is not church complete, because there are some things that it can't do, such as having the ability to not halt. When you introduce a while loop, you get all the power of running for potentially unlimited cycles. And the while rule is the hard one. It's so hard it's got its own slide, actually. While is the hard one. While is always the hard one in everything. And it's because it's the one that gives you that extra computational power. Yeah. With great power comes great responsibility. If you can ever remove a while loop from your code, it's usually a good thing to do. If you have a while loop, always think, can I do the for loop instead? Because with a while loop, you run the risk of your program just spinning into an infinite loop and creating a blue screen of death or whatever. Whereas a for loop should just about always terminate, unless you're doing really nasty things. So yeah, sometimes you need a while loop because you actually need that extra computational power, but it's actually not as often as you think. Okay, so what is going on here? We have a new Greek letter which is called eta. That is the Greek letter eta. It looks a bit like an N, but it's pronounced eta. And this is somewhat mysterious. Okay, there is this cloud of mystery around logic and computation that I hope you have experienced by now. You know, there are some things that are very nice and understandable and easy to define and easy to compute, and there are some things that seem to be mythical and possibly infinite and possibly uncomputable, that float around as well. And eta is one of these things. It's called the loop invariant. Okay, and you know, some of the quotes about eta emphasize this mysteriousness. You know, according to Huth, to choose this requires intelligence and ingenuity. You know, these are the kind of things that are attributed to humans usually, rather than to mechanical systems. It may be automatable if you can build an AI that is good enough to do what the human is doing. But this is thinking outside the system to find out what eta actually is. It's hard to come up with an algorithm for doing this part. And someone, possibly Dijkstra, said to know a while loop is to know its invariant. You know, this is the soul of the while loop. So what you can see in this rule then is the invariant doesn't change. That's what invariant means. Okay, a variant is something that changes, an invariant is something that does not change. So here's our while command. Okay, while b do c. Maybe you want some curly brackets in there, depending on your preferences around curly bracket. But we're saying, is there something that does not change? Okay, every time you go around this loop, you're going to execute the command C. So consider a single iteration of the loop. That's what we're writing about above the line. And what we're saying here is that suppose there's something that doesn't change. But there's the invariant. Something was true. You know, X was red before we painted Y blue. Say C is the command to paint Y blue. So X was red and X is still red at the end. So there's something that the command in the loop didn't touch. There's something it just left alone, and it survived that iteration of the loop. And what the rule is saying then is that if eta survives one iteration of the loop, then it will survive all of them. Because when we look at the conclusion of this rule, look, there's eta at the beginning, and eta is preserved at the end. Okay? So once again, this isn't a full description of what while actually does, but it is an observation about one of its many properties that is useful if we want to try and prove things about a large class of program. So, you know, a slightly more complex example then would be, let's say we're going to paint a whole bunch of things. You know, maybe we've got an array, X, Y, Z, whatever. We're going to go through that array and we're going to paint everything blue, one item at a time, but there's nothing in that array that is, did we start at X? And say we have some other object, omega, and we never touch omega, and omega starts off being red. remains red through any iteration, and therefore at the end of the whole loop it is still going to be red. So the invariant is the thing that didn't change. It doesn't change in a single step, and the rule says therefore it doesn't change at all in the entire execution of the while loop. There's a bit of extra logic here around the B, which is easier to understand. So B is the condition, B for Boolean. You know, while the sun is shining, paint more things blue. So you can see some extra detail. This input only has to work when B is true, because you're only ever going to execute command C if B is true, if the sun is shining. So that's weakening the input condition. Okay, so you don't need this general precondition only of the invariant being true. You need specifically the invariant to be true and B to be true as well. And the other observation that is made by this rule is that when the loop ends, B is now false. That's the definition of the end of the loop. So you can happily conclude at the end of the loop that B is now false. So notice B appears at the top as an assumption. That's an input contract, a precondition, and it appears negated as the post condition, because at this point B's been used and affected, and it's become negative. So this is a very powerful rule. You can use it to prove stuff about while loops, but you can only do that if you find a suitable invariant. So there are many trivial invariants. You know, any loop will not change the fact that oranges are orange, say. You know, oranges just don't enter into most programs. You could put anything in C, and the fact that oranges are oranges will happily be invariant throughout. But that isn't especially useful in reasoning about your program, because you probably don't want to make any conclusions about oranges being orange. You want to make conclusions about the states of your variables. And if you want to draw a conclusion like that, then you're going to have to come up with a new invariant that says something that is actually interesting and useful about the state of your program. And that's where this mysterious intelligence and ingenuity comes in. And this is still an active AI research field. You know, you'll find papers being written this year about here's a new machine learning method to try and suggest invariants. You know, often you'll suggest an invariant yourself and it will be wrong. It won't work, and you'll go through that design iteration again. You know, you'll see why it doesn't work, and that'll be a new idea to try out, and eventually you might find the right one to prove the thing you want to prove. So how do you automate that kind of creative invention process to propose new invariants? So yeah, you'll find people throwing deep learning at this, whatever this year's trendy machine learning algorithm is. It doesn't matter if they work or not. The idea is to be proposing them, yeah, and then you test them using the mechanical logic until you find one that actually works. This is what it looks like when you put a bunch of those rules together to actually try doing something useful. So this whole session is very closely based on the proof chapter. Like most of the examples, I've just taken this straight out of proof. We don't normally write verification proofs in this format because they get very big very quickly. But this example is nice just to show you that what we're doing is just logic. It's the same kind of logic that we've seen in all the other, you know, the mu system, Blandy calculus, first order logic. You know, it's just like all men are mortal, Socrates is a man, therefore Socrates is mortal, right? We're stacking things up, we're drawing conclusions at each step. And remember again, each of these things is just a formula. It's a big string, and you don't have to care about its meaning in any way when you're doing the proof theory. You've got a bunch of rules, like all these systems. You've got a bunch of theorems, and you you can choose how to combine them together to start with the stuff you know to try and get to the conclusion that you're trying to find. Okay, so if we do look within a formula, you know, we can choose to think about the meaning, you know, the structure of the programs underneath, and if we choose to do that, then we can break these things down into preconditions and programs and postconditions. So here is a Hoare triple. And can anyone explain what this theorem is actually saying? So this is a theorem because it has a proof. This whole thing proves that it's a theorem. So what does this theorem actually tell us that is useful?
It says, given any state, that's the t, we have a program where y equals 1, z equals 0, while z isn't equal to x, we increment z, which allows us to halt eventually, hopefully. And then we say that y equals y plus z. So we're going to, oh, no, times z, because it's factorial.
Times z, yeah.
Okay. And that means that we multiply everything from 0, from 1, because we increment at the start, from 1 up to...
oh, good. Yeah. We started with z0, but we incremented it before we used it. Yeah.
Yep, of course, because otherwise all of factorials would equal 0, and that would be very unfortunate. Yeah. So, and then the postcondition was that we will have calculated, or rather, we will have put into y the factorial of x.
Okay. Good. So yeah, this is a proof that this program, if it terminates, will end up with y being x factorial. Yeah. So remember, we're only doing partial correctness, so we haven't said anything about whether or not it terminates. That's to do later on. But yeah, if the program terminates, and our logic is good, we can then be absolutely certain that this program really works. Yeah, this program, if it terminates and our logic's fine, it really will compute the factorial function. Yeah, so if that factorial function is needed in the nuclear reactor, we can now be almost certain that it's going to do what we really want it to do. And you know, almost certain now is really just dependent on us being confident in our logic. So if we assume we're going to use a system, both a system of logic and a software implementation of that logic, you know, if we assume that those things have been used for many decades by many hundreds of thousands of people and no one's ever found a bug, we can at least push all our software engineering worries into the states of those systems rather than them being in the reactor control system. You know, our reactor system works as long as the theorem prover works, and as far as we know, the theorem prover works, but we can never be absolutely sure. Okay. Oh, Gary?
Sorry, Charles, probably a silly question. On the top row, I see a factorial sort of sign there. Is that sort of saying, I don't quite get how if this is a factorial function, are we permitted to use it there at that stage because we haven't sort of...
Yeah, so you can say whatever you want in these preconditions and postconditions. These are just mathematical statements, so they're not part of the computation. If you actually write this program out, which we'll do in a bit, that is the program. That's all the program is, and that's the thing that's being verified. So there's an exclamation mark there, but it's not being used as a factorial. Right? It's being used as not equal. So where you see the factorial here, for example, this is just a mathematical statement. This is just saying that if this thing was the case, mathematically, then the effect of this little program would be to make this thing true over here. So yeah, that is actual mathematical factorialization, whereas this thing is a particular program that you're hoping is equivalent to the mathematical operation, and that's the thing that you're trying to show. Yeah. So yeah, we're not defining mathematical factorization here. We're assuming we already know what mathematical factorization is, and we're trying to make sure that our imperative program actually does it. Hey, wouldn't it be really nice? Wouldn't it be really nice if your actual mathematical definition of factorization was a recursive function, and then you could have a language where you just wrote down that recursive function directly, and then you wouldn't need to do any of this stuff because it would just work in the first place. Yeah.
Well, it's interesting that we don't have to make any statements about factorialness, but we do have to make a statement over on the far left about us assuming in the first instance that 1 is in fact equal to itself.
So yeah, this is a nice example of the implication rule. Okay, so you remember I said this makes more sense in a real proof, right? So the implication rule doesn't change the command at all. It's just fiddling with preconditions and postconditions. So truth, which way around is this? Truth implies 1 equals 1, right? So you're allowed to make that substitution because one of these things follows from the other. So this is something, probably this has emerged from down below. Usually when you make these proofs, if this was a big module, we'd spend the whole of it actually trying to make proofs of a whole bunch of things. Usually when you make a proof, you start by writing out the thing you're trying to do. You write these proofs from the bottom up, literally from the bottom up. You write that down at the bottom of a big piece of A4 paper, if you're doing it by hand. And then you you use your creative judgment to choose what rules to apply backwards to try and form it. So some of this is easily mechanizable. So in particular, you can see this program is obviously a composition of small programs with these semicolons, right? You've got an assignment, and a while. So the obvious first thing you do is you split that up because these compositions are very easy to break up, right? So the first thing we've done, or whoever made this proof, Mr. Huth presumably, the first thing Huth has done is split this into 2 programs. He's saying program 1 does a bunch of assigning, program 2 does the while. And by that composition rule, which is applied here, remember the post condition for the first bit of the program has to be the same as the precondition for the next bit. So they've split that bit up there. That's the very easy way to make the first 2 lines of the proof, working from the bottom up. Then they've done the same thing here, right? This program is actually a composition of 2 little programs, so it's easily automatable to split that up into 2. So now you need this to be true and you need this to be true. And notice the post condition there's the same as the precondition there. The point of that, to answer your original question then, is that is why we ended up with this particular precondition and postcondition. You see, we've got truth there and we've got y equals 1 over there. So we didn't choose those to be the precondition and the postcondition. They've been forced upon us because we started off with something we were trying to prove, and this is required. So this thing isn't a self-evident statement yet. So at this point, you have to use that implication rule to turn it into something that is self-evident. So you're trying to prove this. You're almost done. And the last thing you need to complete the proof is just to replace that true. Because the world is true, you can write down anything that is a tautology. You could say true. If you want to do it in the model theory, you'd say true entails 1 equals 1. Right? If you're in a world that is sane, then 1 must equal 1. There are many things that are entailed by being in the top T world. So if you're in that world, you can. If you're going this way, you are weakening the precondition. You're saying I'm only going to consider one entailment of that truth and write it there. And this is the one we've picked to make this whole thing nicely self-evident. Okay. I'm not sure if this is necessary. Actually, it depends how you actually implement your system and what you consider to be a self-evident statement. So the author here has assumed that is a self-evident statement, but that this one isn't. I'd probably argue that this one is all you need, really. Isn't it just obvious that if you make y equal 1, then y equals 1? It doesn't really matter what the precondition is. But if you're implementing all this computationally, sometimes you have to break things down to a level that just looks silly to humans. You might have a rule that says only things of this form are actually axioms of the system, and so you need to go to the extra level to complete the proof. Shall we have a look at some more bits of it then? I think that's a nice journey through that part of the proof. So again, if we've constructed this from the bottom line going upwards, yeah, we'd have ended up with this part here, I think, through that process. So here we've ended up with something a bit strange because our precondition here is all about y. It says y equals 1, and that's there because we've inherited it from the thing that we're doing over on the left. Remember, the composition rule says that this guy's postcondition has to become this guy's precondition. So we have to do some work to tidy this up because the command here is all about z, and our precondition's still talking about y. So the rule of assignment, I think, lets us write this down. We've made z equal to 0, so therefore we can add that fact to the postcondition sitting over there. So yeah, again, as a human, that is probably self-evident. Yeah, as a human, you'd probably stop there and say, yeah, that works. If you're automating all of this, you might have to take this extra step to change the precondition and the postcondition to make something that is so obviously true that even your mechanical system is able to recognize it. So that's the easy side. That's just assignments and composition. The hard side is the while, because while is hard. So, but all of this stuff has got dealt with over here, and that has resulted in a postcondition. And the rule of composition is that postcondition has to show up as the precondition over here. So this is now given to us for doing our thinking about the while loop. Our postcondition for the while loop is given to us from the conclusion. So we've been given a precondition and a postcondition. Now we have a simpler task that we've just got to verify this single while command. Actually, it's not that simple because the while command itself has a little program inside of it. Yeah, this is all going to recurse out. And at this point, you have to put on your human creativity hat and choose an invariant. You have to meditate upon the meaning of whileness and on what it is you're trying to prove and on what is interesting and relevant, and choose an invariant that has all that information in it. And in this case, we're just going to give you the invariant because it's written there in the proof. You know, hey, we're not going to do this in the exam, by the way. If this was a hard exam, we'd give you a bunch of these, and the task would be create the invariants to make the proofs work. But in this case, the invariant is just that y equals z factorial, which is different from it equaling x factorial. Yeah. So y is a temporary. Sorry, z is a temporary variable. So you know how that is done, we will leave to the mystery of human creativity for now. Yeah? If you want to do a PhD in AI applied to verification, that's still a great thing to study, as far as I know. So now you need to show that that invariant matches the precondition that we actually have. Okay, so remember we were given this precondition that's propagated from what we did before, and we want to have the invariant here. So you've now got to use the rule of implication, and you can apply it on both sides at the same time. You need to show that this follows from this and that this follows from this, using the rule of implication. At that point, you're just doing regular logic, right? You're trying to show that one of these logical statements implies the other one. So there's nothing specific to computer programming about it. So in fact, the Floyd-Hall rules are really an extension of whatever other logic you're using. You know, at this point, you're going to call out to your propositional logic or your first order logic or whatever, and just do normal logic as a subcomponent of your Floyd-Hall system. So, you know, assuming you were able to magically pull this invariant out of the air, then you know, now you're nearly done. Now it should all be fairly mechanical again. So here we're going to invoke the rule of while, and the while loop says that in order to prove this stuff, you consider a single iteration. So you know, this rule introduces the while keyword. So if we're going the other way, we're removing the while keyword. So to prove a single iteration, you need your invariant to be there and you need it to be there. And that's just the condition for termination. That's come from down here. And now we have a simpler problem, okay? We've eliminated the while statement, and now we just have a really simple program that just does an addition and a multiplication. You can see this has the structure of a composition, so we invoke the rule of composition here. And as before, that lets us peel off this part of the program from this part of the program, and this post condition has to match this precondition, and then everything's easy. It's just the same as we did over here. Okay, so you know, that's roughly how a human would go about constructing a proof like this. And if we were going to do a hard exam, this is the kind of thing we'd give you. You know, prove that this factorial program actually works, and invent all of this stuff above it. And you know, what was interesting about that process is we generally work from the bottom to the top. Parts of the process were clearly mechanical, so in particular these compositions are very easy to separate, and you know, just turning the handle pretty much got us all of that, and it got us to here, and all of this we did by turning the handle. But when we got to this bit, we had to use some human creativity to pull an invariant out of the air. And there may be, in larger languages, there may be more creativity involved in deciding which rules to apply in what order. I think in this particular language, it's fairly obvious because the compositions come apart, and if there was an if in here, the if would come apart, and it's only sorting out the while that's difficult. But if you're in a situation where there are many different rules you could apply at each time, you know, like in the lambda calculus where you're deciding which part should I reduce when, then you might have a bit of human creativity there as well. Gary.
Just a quick question, Charles. Can we sort of keep these in our back pockets and use them when we come, let's say, something larger than a factorial function, and then say plug this into that section as we're proving a broader program?
Yeah, absolutely. So, you know, as with all these logics, once you've proven not just a particular theorem, but if you've showed that this pattern of theorem proving always works, yeah, you know, now you can put this, you can actually include it as an extra rule. You can put a new rule in your logic that just says, whenever you see this pattern, this works. You know, you're basically gonna take this whole thing and add it as an axiom, effectively, to your rule system. Yeah, good question. That's exactly how a real proof system is going to work, because you don't want to figure this out every time someone puts a factorial function in their code. Yeah, you want to do that once and then be able to pull it out. And that's called a tactic, by the way. When you see serious theorem proving systems, they will have a whole bunch of these pre-prepared tactics, and they'll try and make decisions about which tactic should I try out. In the simplest case, a tactic is just trying one of the basic rules. But as you come across stuff like this, yeah, now you've acquired a factorial tactic that you can pull out as a single thing. Good. You can see this notation is going to get out of hand, right? This is a tiny little program. It's only got 3 or 4 lines, depending on how you like your curly brackets, and it's already threatening to expand off the edge of a page of A4. So you always do this on landscape A4, by the way. If you do it manually, you take your pad and you rotate it, and you write this on the bottom of your landscape A4. And it's confusing because all the lines are now going vertically on your page, but you need a ruler to draw these big lines going along. But it doesn't fit if you do it quadric. Yeah, spent far too much time doing that a long time ago. So look, what we do in practice is we do exactly the same proof, but we use a nicer notation. So this is not the same proof. This is a proof of the one we did before, right? Do you remember the one we did with the A and the X? And here I actually got it right because there was a typo in this before. It said A. This is the one that just makes y equal to x plus 1. But what we have here is, this is more like the Fitch notation for proofs we've seen. Instead of writing them as a tree and using a ruler, we're going to write them as a sequence, and every time we apply a rule, we're going to write the name of the rule. So this is like how Gary solved the MIU problem, by writing the proofs as programs. So what you see here is there's kind of 2 ways to read it. One way is as a series of program annotations. So when we talked about software engineering and contract-oriented programming, you can read this simply as a set of comments, effectively, that have been interspersed with the main program. Okay, so you could actually write this in your program file, in your text editor, assuming you have some way of putting in these funny or brackets. You could write all this stuff in, and you know your C compiler will just ignore them. It will treat them as if they're comments. Okay, and they're effectively functioning as assertions. You could equally well interpret them as dynamic runtime assertions, and then go around asserting them every time the program runs. The other way to read this is as a alternate notation for a tree proof. So if you read it this way, the program lines are really just strings. You know, they're not the interesting bit. They're just the strings that the proof system is operating on. There's the curly bracket. And the interesting bits are the preconditions and the postconditions. So, and the names of the rules that have been applied at each point. So together, these things are equivalent to the tree structure that we saw over here. And a nice exercise for you guys actually would be to demonstrate that. Yeah, why not do this as an exercise? Go turn this into what is called a tableau notation and try and turn this back into a tree proof again. So they're completely equivalent notations for how the proof is being done. Yeah, and the nice thing about this form then, well, one is that it now fits on a normal piece of A4 paper that hasn't been rotated by 90 degrees, but also it fits into our practical programming methodology. You're actually going to write these now in your program. You're going to open up your Vim and write your C code and write a bunch of these extra comment lines with assertions all over the place, and then use a tool to go and make sure that they actually hold up. Okay, that's partial correctness. When we go to total correctness, we need an extra bit because we have this problem of termination. And remember, proving whether a program halts or not is an uncomputable problem in general. But in many everyday cases, it's fine, and you can do it. Okay, it's only the general case that is impossible. So when you have a need for total correctness, you replace your while rule with this one. This is called the total while rule, and it is exactly the same as the partial while rule, except for having these extra conditions in the blue. Okay, so as before, eta is the invariant. Let's use some different colors. So look, there's our invariant. We're saying if the invariant holds on any one iteration, then it holds here, eta typo. Then the invariant also holds for the whole thing. Okay, that's just as it was before. That B and that B are exactly as they were before. They're just checking the Boolean truth condition. But then we have this new thing, E, and E is called the variant. Remember we said there are invariants and there are variants. So a variant is something which does change during the loop execution. There wouldn't be much point running a loop if it didn't change anything. Yeah, if everything was invariant, there's no point in doing the loop because it has no effect. So yeah, something should be changing when you run a while loop. And in fact, if nothing's changing when you run a while loop, that's a good source of bugs. That's when your program is likely to get stuck in an infinite loop because nothing's changing. There's nothing to make it stop. So the variant is basically a counter. The variant is basically a positive int. Let's say we found something that is related to the number 5. It doesn't have to be a specific variable in the program, but there's got to be some function of the state of the program which equals some number. And we're trying to prove that something like this exists such that every time you go around the loop, this number decreases. So it's going to go 5, 4, 3, 2, 1, 0. And when it gets to 0, the program has to stop. So a way of expressing that is to say that there's something called E, not necessarily a variable, but there's some number that exists as a function of the state of the program. And it starts with a number, let's call this E0. It starts at some initial value. That's this statement here, okay? It starts at some initial value and it always decreases and it is always greater than or equal to 0. So if it carried on decreasing beyond that, it would go below 0 and that would violate our conditions. So E must always decrease and it must always be greater than or equal to 0. So this rule says that if you can find such a thing, if you can go and find a variant as well as an invariant, and if you can prove this property, if you can show that it's always ticking down, and it's always greater than or equal to 0. If you can do all that, then your loop is guaranteed to terminate. Because roughly it's going to behave like a for loop. You know, it's like for I equals 5 to 0, and then stop. So as with the variant, this is going to require heavily quotation marked intelligence and creativity to figure out what this thing is. You know, you're going to have to invent it and then prove that the thing you've made up actually does what you want it to do. As with the invariants, this is a AI research field. How do you try and at least suggest ideas for invariants? If you have a suggestion, it's very easy to test whether it works, but the hard part is creating the suggestion. And we know, we've already proved that this is uncomputable in general, right? Because it would imply that you could solve the halting problem. So it turns out finding both variants and invariants of both of those is provably uncomputable. I'm not going to give you the proof for the variant one because it's quite complicated. But both of these tasks are generally uncomputable. But in practice, you can often come up with good heuristics for guessing what they might be. So those heuristics do actually exist and are implemented. So I'm going to give you, instead of a reading this week, I'm going to give you a video to watch, which is a presentation of a C verification tool, so VCC, Verified C Compiler. So this is, I think, still in development at Microsoft Research, which is not quite the same thing as Microsoft. Sometimes we quite like Microsoft Research, and it's open source, but it's open source in the sense that it only runs in Microsoft Visual Studio with a whole bunch of you get the idea. But there are very good academic researchers in this field sitting over there, and it's a nice example of a almost usable tool. You know, this is something that in 10 years' time is going to become part of Visual Studio Code, is the idea. So what we're going to see in VCC then is, you know, creating these proofs by hand is tedious and also error prone. You know, proofs are often longer than the programs, so let's use some AI to automate at least parts of it. There's going to be times, you know, as with Gödel's theorem, there's going to be times when the AI gets stuck and it has to come and ask you as a human to help. And it's debatable whether your capabilities as a human are really any better than the AI, but that's the best that it can do in those cases. You know, so at least for a long time, this has been done as a interactive process with the AI doing as much work as it can, but then these highly paid career humans coming in and doing the human part of it. Some of those guys' jobs are now under threat because the machine learning ideas are starting to make better and better suggestions. I suppose there's still jobs for the people who design the machine learning systems. Right? So you know, we see this gradual application of AI, you know, beginning by just checking the proofs, which is easy. You know, then you go to filling in proofs. You really don't want to have to go through your code and write every single one of these by hand. Okay, that would be very tedious and very error prone. You know, what you'd like to do, ideally, you'd just like to write your precondition and your postcondition, and then ask the AI to fill in all the rest. Now that's hard. So in practice, you're probably going to write a precondition and a postcondition, and then maybe you're going to write a couple of these other things. You know, maybe you put in this one and this one, and you're going to put in enough hints that the AI can figure out what all the other ones are, because a lot of this is fairly mechanical. And then the strongest version of this is automating the invariant finding, of variance and variant finding. So when you see this compiler work, I think a lot of the time it's still going to come back at you for what you want the invariant and the variant to be. But in some cases, these systems are starting to make their own guesses now for what these are. So this used to be considered AI. Now it's almost working and is almost just going to be something that drops down in Visual Studio. AI isn't called AI when it works; it's just called computer science. It just becomes verification. AI that actually works becomes computer science. So I'd like to give you this video to go and watch the thing in action. It's better for you to get it directly from the authors than from me. So using systems like that, we are now starting to verify big, real stuff. Okay, so VCC we mentioned was developed for the purpose of verifying Microsoft's own hypervisor, Hyper-V, and it is in use for that purpose. So the hypervisor is the thing that lets your machine appear as multiple separate machines. It's what enables cloud computing, right? Multiple people using a single machine, and almost at the level of bare metal hardware, it is appearing as if it is several different machines. And that obviously has to be very, very secure, because your $10 billion cloud computing business isn't going to last for very long if someone finds a security flaw that enables them to go and read the data of all the other people using the computer that you're running on. As recently happened with the Spectre class of bugs. Other big chunky systems include a C compiler. So VCC is a C compiler which does verification of your code built in. Okay, VCC itself isn't verified as far as I know, and in particular, it can't verify itself because it's not powerful enough to do that. CompCert is a C compiler which is itself verified. Okay, so you understand the difference? So CompCert isn't going to verify your code like VCC does. CompCert is a C compiler that really, really works and does not have bugs in it, because every line of the compiler itself has been through this process to prove that it actually works. The bugs in compilers are some of the very nastiest bugs in the whole world, because very hard to track down, and they affect a lot of people, and they make those people very, very angry, and they can lead to very significant security issues. Once the bug becomes known, it's going to be exploited in many cases. So CompCert is serious enough now; it will give you C99 compatibility and compile to all these different backends, and it really, really works. Oh, and it's optimizing as well. It's almost as fast as GCC, but not quite. And then recently, this is getting scaled up all the way to operating systems. So SEL4 is a fully verified microkernel. So microkernels are good architectures to use with verification, because the microkernel is relatively small. You wouldn't want to verify the whole of the Linux kernel, because that would be everything. But in a microkernel architecture, you have one little bit, the microkernel, that is doing the absolutely crucial stuff, and you let everyone else worry about their stuff separately. We're not going to verify all the printer drivers, or if the authors of the printer drivers want to verify their code, it's their problem to go and do that. But verifying the microkernel is a very good idea. So this is around 9,000 lines of C code, another 600 lines of assembler. You can read about it over here. And you notice these are all verified with different systems, right? Hyper-V was done with VCC. CompCert was done with a system called Coq, which is French, and you have to get your best French accent on to avoid it sounding rude in English. They're currently planning to change the name for that reason, or some of them are, and they're all having a mass debate over that right now. And SCL4 has been verified with a system called Isabel, which is written in ML by my old director of studies, Larry Paulson, the same guy who wrote the book ML for the Working Programmer. So this is an English approach, this is a French approach, and this is a Microsoft approach. You can take your pick. And you know what's really neat is if you can use these verifying tools to try and verify one another, because remember, no tool is able to verify itself. That's the whole point. Okay. Again, this has gone on for quite a while, so I'm going to give you this more as homework than as workshop. For the remainder of the semester, I would like you all to be thinking now about question 1 on assessment 1, which is this: model and solve a problem. It actually says in AI or verification, but let's try and do the verification route. Question from David?
Yeah, I'm still writing question 2. I might need a bit of help on that front regarding just like with regards to how lambda calculus stuff works.
Okay.
So if you could like organize a meeting for that or something at some point, that'd be great.
I'm planning, I think next week we'll try and keep the lecture part quite short, and then we'll have time to go around and look at everyone's stuff, if that's okay.
Okay.
With the
Yep.
workshop. I
will try to get some more of it done before then, obviously, but yeah.
Yeah. I wanted to rush to get this to you guys now, because this is what you need to start working on the other assessment questions, so we can slow down a bit after this week, I hope. Yeah, good, okay. Good. Thanks for letting me know. Okay, cool. So let's assume we're going to attack this question as a verification question, and I hope you can see now how they're really the same thing. You know, there's a lot of AI, well, there's a lot of working AI, now known as computer science, in these verification systems. So a really good way to do this is to try and use VCC. If you watch the video I've given you as you're reading, as well as the Visual Studio version, they have also put on a small cut down version as a web-based system, which you can access here. And this means you don't have to install anything. Now, this has been a little temperamental recently. There were a couple of days last week when this system was running very slow. Yesterday it was okay, and a couple of weeks ago it was okay. If it's doing this again, then we might have to come up with another plan. So let me know how the system works out for you. There is a larger tutorial document on the system here as well. There are some very nice examples built into the web system. You'll see there's a Hello World program, and there's an adding program, and a couple of other things. And you can really just click on those examples and then mess around with them. You know, try adding in a few extra lines to see what they do. So look, this stuff is hard, right? It's still a research system. It is not anything like the Visual Studio or the Vim that you use every day. Yeah, this is coming out of a research lab, and you need to respect it in that kind of sense. So we're not going to be verifying Space Invaders or anything in this. What we'd like you to do is just try and show really the smallest possible case you can of verifying a little tiny bit of your own code. Okay? And by a little tiny bit, I mean tiny. You know, I mean tiny in the sense of the programs that we've seen in an example like this, or in an example like this. Yeah. So you know, it has to be different from what other students are doing, because we have plagiarism rules for this stuff. You're welcome to help each other out, but I would suggest something like take a bit of your own third-year project code. Take what's the smallest function you have in your third-year project code, If you're not already in a C-like language, then port it to one. VCC is C just about. Port it to that subset of C, and it's probably just going to be something that adds things and multiplies and has a while loop or a for loop or an if statement or something. But to show that it's original work, it would be really cool if you really take a part of your own code and actually say that in the report. Give the reference to your GitLab third year project and say, here's a little bit of code I've taken from my own work, and I'm going to do a novel verification of it using VCC. Okay. So this can run all through the rest of the semester, well, at least when you finish your lambda calculus stuff. It's not easy to do this. We can spend more time in the workshops helping people out with it. Note the assessment isn't just a software thing. There is also a bit of thinking and writing as well. So the assessment also asks you to explain what this is actually doing. Tell us a little bit about what you've learned in this lecture and try to link it to what you can see going on in VCC. So it would be really neat if you could give some little fragments of the VCC work you've done and then make the links to material from these slides. How is VCC different from these other systems? This is a university thing. If you've noticed, all the third year modules have to have this thing about comparing and evaluating and contrasting. So, if you weren't doing this in VCC, what would be the alternative? For example, how does this process compare to running unit tests on the same piece of code? That would be a very nice way to show an alternative and a comparison. Okay, so please study this slide in a lot of detail, because this is how we actually get some marks for you. Okay, so yeah, I know this has also been quite long. I hope it should get easier now. I think this is everything you need to actually pass the portfolio assessment. So we're going to look at a few more topics. I think next week we'll maybe talk a bit more about these proof systems in practice to help with the assessment thinking as well. And then we'll look at a few more applications of logic and computation. Gary.
Charles, would you mind at all if we chose a snippet of our code and brought it in, maybe just for general discussion in the workshops? Would you be okay with that?
Yeah, that's absolutely what they're for. Yeah, as long as you're not submitting the same. Actually, technically, it is okay to use the same piece of code. You must submit a unique piece of writing for the portfolio exam, but it's actually okay for you to work together on the verification as long as you write it up completely independently of one another. So yeah, you might want to do that. You might want to get in little groups again and just pick one person's code. The important thing is to show that you haven't just copied the whole thing off the internet, right? So by using a piece of code from at least one of your third year projects, then you can demonstrate that this is an original thing, and you haven't just pasted a whole load of VCC tutorial. So yeah, okay. I don't mind if you want to do that. If you want to work together and write it up independently. To be honest, I think if you're working together, it's probably going to be just as easy for you to help each other verify each other's own code because it is to all puddle down around one. But we'll see how it goes. Yeah. The underlying point is to learn how verification works and get some experience of it, and that's what we're assessing it for on the CRG. Okay. Good question. So yeah, otherwise, yeah, let's try and make a bit more workshop time from next week, and see you next time. Bye for now.
Awesome as always. Thank you very much. Thank you.
See ya.